the last class on Friday, we started discussing about hy- hydraulic turbines. So, if I can quickly recap that what we discussed on Friday in Friday's class. So, basically, turbines are used to convert the mechanical energy which is available in rivers, whales, or any other means into useful electrical energy through a generator which is attached to a rotating shaft. So, a rotating shaft in case of pumps, we call it impeller or propeller, while in the case of turbines, we usually call it runner. So that rotor blade and shaft, those things are called that assembly of rotor is called runner in case of turbine. So then we discussed about different types of turbines with respect to working fluid. So in case of hydro turbines or hydraulic turbines, water is the working fluid, like in all the dams, like Sarvela Dam, Manga Dam. Then if air is the working fluid, we can call it wind turbines. And then we use steam turbines in steam power cycle and gas turbines in gas power cycle. So steam power cycles, they are steam power cycle and gas power cycle. They are usually used in industry for the generation of electricity, but gas power cycles, they are also used in aero application, like the engine of an aeroplane that has got gas turbine installed in that. So then we have got the efficiencies for the turbines are usually higher. So we discussed that there are many reasons for that. Like rotational speeds are higher in case of pumps, while they are lower in case of turbines. So we would have lower frictional losses in case of turbines. Then conversion of flow pressure energy into kinetic energy of rotor blades in turbines, they have less losses, and additionally the hydro turbines, they are usually of larger size, so viscous losses are less important. And then turbines are also designed to run for a specific volume flow rate of the fluid, so that we can design a turbine to have maximum efficiency. So these are some of the reasons because due to which we have got higher efficiency in case of turbine. So after that, we discussed that there are many application areas of turbines. One is volume flow rate measurement, but that is quite limited scope for that. Majorly, we use it for the generation of electrical energy, electrical power, right? Electricity, basically. So then we discuss about the types of turbine with respect to net head and volume flow rate. So for that, if you remember that in the last class we discussed impulse turbines. So Pelton wheel is an example of impulse turbine. So it requires higher head, and it can operate on lower volume flow rate. And usually because there is an impulsive force which is created due to change in direction of the fluid rather than the impact. So the pressure decrease only happens in the stator stage. There is no pressure drop in the rotor blade because there is no kind of tracking of fluid. It is more kind of change in momentum due to change in velocity direction. So that's why we assume that there is no pressure decrease in the runner. In effect, if we talk about the practical situation due to frictional effects, there would be some pressure losses, but for the ideal case, we say that there is no pressure decrease in runner. While in case of pressure turbine, the head requirement is low, but it needs higher volume flow rate of fluid for its operation, and then pressure decrease occurs partially in stator blades and partly in rotor blades. So the practical examples of hydro turbines for reaction type that are Francis and Kaplan turbines. So we are going to discuss these two turbines in this class, and then the last topic would be the hydroelectric turbines which are used for the power generation in dams. So we would see that how the general functionality of a dam, like we can see that what kind of turbines are there and how water flows through that dam. So that all that schematic we are going to discuss maybe today and in the last lecture of this course, which is going to be held on this Friday. So Now, with this introduction, the pattern we discussed in the last class. So now we are going to discuss reaction turbines. So for the reaction turbines, the first type is we can call it the Francis turbine, or so if I can show you the figure, let me show you the figure here. Just a minute. Okay. So if you can see it on the whiteboard, we can see a kind of centrifugal pump arrangement. But here, the direction of flow is totally reverse. So if you remember that in case of pump, centrifugal pump, the if you can please hold for a minute, I have got an official call which I need to take. So I will. Sorry for the interruption. It was an official call which I had to take. So, as I was discussing that here, in case of centrifugal pump, usually the water comes from this impeller eye, and then it goes outward radially, and then it goes out of this. But here you can see that the fluid is coming tangentially from this from this pipe, and then it would come into this first row of blades, which are called, we call it the stay vanes. Stay vanes mean that they are not going to move. Then it would go towards the second row of blades, which are called, we call them, let me write it here. Okay, it is written here, stay vanes, and then wicket gates, which are movable, right? So there you can see two rows of blades here in circumference. The first one, it is stay vanes, which are fixed blades. Then we have got wicket gates, and we also call them guide vanes. Okay, so we call it wicket gates or guide vanes. So what is the function of this stay vanes? They are just to reduce the swell of flow, so that it would reduce the swell of flow, and then it would move the fluid towards the wicket gates, which are also called guide vanes. And what is the function of guide vanes? That first first function is that they ensure that fluid enters the runner at optimal angle for maximum power extraction. Right, so they kind of make sure that the fluid which is coming from here, it would go in a best direction, which would give us the maximum power. And then the second function of these guide rails are to control the volume flow rate. Control the volume flow rate. So that because they are adjustable, so they can close or open depending upon the volume flow rate which is coming through this entrance, right? So, and then we have got runner blades, which are shown by these black lines. So these are the runner blades. And then this is the shaft on which runner blade is attached, and then the generator is attached to the other end of that shaft for the power generation, right? So this was just a schematic. So let me show another video for this to tell you about the. It would give you a three-dimensional view, and it would elaborate the functionality of this process turbine, and then we would take it from there. So let me share the video with you, so then you can. So let me kind of explain it, and I would explain it as along the way. So here you can see that the water is going to enter from here, from this side, and it would be moving like this, and there would be tunnel attached here. So as the video would be played, you can see that assembly maybe in a while, and then there is a draft tube here. So here, if you see that the cross-sectional area is less, but for the draft tube, it has been increased. So if you remember from your thermodynamic knowledge that when we increase the increase the area, then the velocity decreases, and then the static pressure increases. Okay, please give me 1 second again. Sorry for this. I have got. Okay, so I'm going to play this video now. So okay, so you can see these here we have got these blades. So they are kind of those wicket uh, wicket gates, or we can call it guide rails as well. So these blades from where it is entering, and then here there are certain blades which are runner blades on the bottom. So water is going to enter from here, and then radially, and it would be discharged axially downward. So this is the cross section he is talking about. That this is an aerofoil cross section. So in aerofoil, we know that that when the fluid comes, there is a high pressure side and low pressure side. So there would be in this, if the fluid is coming this way, this would be high pressure side. This, and the upper side would be low pressure side. So there would be a net lift force. In this case, it would be kind of providing the force in the angular momentum direction, right? So that lift, it is not going to lift it, but it is kind of providing the torque for this shaft to rotate. Yes. Okay. So what does it mean that here the fluid is coming from here, like this from the bottom, and then it would also first it would hit this blade, which would produce lift force, and then because the direction of the blade would also be changed, so that change in direction would also impart an impulse force. So due to that, we can say that facet turbine is 50% action, so which means that 50% force is due to action, and the rest of the 50% is due to impulse. Okay, so in case of Pelton wheel, if you remember that there was no pressure change in the runner blade. There was only change in kinetic energy. So in impulse case, we assume that there is no pressure change in the pressure decrease in the runner blade. So and all the momentum which is being transferred to the blade, that is entirely due to the change in kinetic energy of the fluid, or we can say that that is due to change in direction of that fluid which is passing through the runner blade. Okay, one thing you can see here that we have got at the entrance, the area cross-sectional area is more, but when it moves tangentially in the scroll, that cross-sectional area decreases. So it behaves like a nodal effect. So it means that the velocity of the fluid increases as it moves along the scroll. So that when it strikes the rotor blade, it would have maximum kinetic energy. So we basically put the draft tube to increase the static pressure at the outlet so that the possibility of cavitation that can be reduced. That can kind of affect the life of this whole assembly very much. So that's why we want to minimize the possibility of cavitation. So now if I can show you some pictures of actual turbine, which is Kepler turbine. So let me share that. Maybe I can share the my second screen. So here you can see the actual turbine, and you can see actually the size of this. This is quite big. Uh, So uh, the Francis turbine that was first proposed by the scientist named as James B. Francis in, I think, at the end of 19th century. So he developed it in 1840. So it means that it's like 180 years it has been in operation. So that is one type of reaction turbine. There is another type of reaction turbine or example of reaction turbine, that is we call them propeller turbine, or we also call them Kaplan turbine, right? So uh, they are kind of this shape. So the Kaplan turbine is somewhat like an axial flow fan running backward or in reverse, like a window fan spinning in the wrong direction due to gust of wind. So that is kind of, you can see that this is also of quite huge size. And then what is the difference between these two types of turbines? They are usually these Kepler turbines. They are First of all, they are axial machines, while this is kind of mixed flow machine. Mixed flow machines mean that the fluid comes in the radial direction and goes out in the axial direction. So that is mixed flow machine. While this Kaplan turbine, that is kind of axial machine, that the fluid comes in the axial direction, inlet to the plate, and then go out in the axial direction as well. So it was again given the name after its inventor, which was Victor Kepler. So it was also at the end of the 19th century. So it has been also operational in like more than a century. So, and then there is another difference between Kepler turbine and Francis turbine, that Kepler turbine, they need the minimum head, right? But Francis turbine, the head requirement is a little bit more, right? So if we kind of see the head requirement, the maximum head is required by the by the Pelton V, and then the second most head requirement is for the Francis turbine, and then the minimum head requirement is for the this Pelton turbine, right? So now we can also kind of have different types of turbines, reaction turbines, eh, with respect to the angle at which the flow enters the tunnel, right? So there you can see that there are four types which we can subdivide the reaction turbine in. So we are going to discuss all these four types one by one and see that how the flow direction towards the tunnel changes in each type. So you can see Francis radial turbine, Francis mixed flow turbine, propeller mixed flow turbine, and then propeller axial turbine. Right. So if I discuss the first type, which is Francis radial flow turbine. So here you can see that because the flow is entering in the radial direction, right? So this is the radial direction, and then it is going out in the exit direction, right? So, but because the entrance is kind of radial direction, so we call it entrance to the runner lane. Okay, one thing, if I can maybe a little bit make it more visible to you. So here you can see one is this wicket gate here, right? And then here you can there is a thing, there is a part which is called band. So this is a cover type which is shown here. So let me show you that what is this band. So if I show you the figure, maybe here, this is the band. So it means that the runner blades, they are kind of in they are kind of surrounded by a ring type shape which is called band. So usually in practice in the field, any turbine which has got this kind of band around it, runner blades, that would be called facet turbine, right? On the runner. So that is the usual terminology we use in industry to specify facet turbine, that we have got a band here. Yes. Any question?
सर ये जो रिएक्शन टरबाइन है
जी जी मैम।
सर इसमें सर वो फीड कैसे करते हैं सर स्टीम को
क्या चीज?
वो स्टीम ही घूम रही स्टीम जो है स्टीम स्टीम
स्टीम
प्रेशर है उसकी वजह से वो रिएक्शन टरबाइन
नहीं,
सर गैस
पहली बात,
रिएक्शन टरबाइन के अंदर सर
अच्छा उसको क्या क्या चीज सा करते हैं, फीड किस तरह करते हैं?
वो जब रिएक्शन सर जो चीज फ्लूइड उसके अंदर इनपुट होगा सर जो भी स्टीम बेसिकली यूज होती है आई थिंक सर उसके
मेरे
अंदर
हम क्योंकि
हाइड्रोलिक
हाइड्रोलिक टरबाइन की बात कर रहे हैं ना, तो वाटर होगा इनपुट, ठीक है। मैं पहली बात, अच्छा
यस सर वाटर
जी
यस सर
जी
सर वो बेसिकली बेसिकली लिक्विड एक तरह की चीज फ्लूइड यूज होगा ना सर जब फ्लूइड बैकवर्ड जाएगा और वो फॉरवर्ड होगा सर सर फ्लूइड उसके अंदर कैसे करेंगे सर वो कोई लीकेज नहीं होगी
ये मतलब अगर मैं आपके साथ एक स्क्रीन शेयर कर दूं दोबारा, हाउ द फ्लूइड एंटर्स दिस रनर, इज दैट द क्वेश्चन उमैर?
यस सर Yes,
Can
sir.
you see this screen on which we have got a pipe like structure in here? Umair?
Yes, sir. I
Okay, so you can see this that fluid is going to enter from here tangentially, and then it would move through this spiral shaped roll, and then from here it would go in the radial direction towards the runner blade. Okay, does it
yes. सर ये
provide
बस टरबाइन नहीं होगा?
while that? What is the difference between impulse and
सर ये
reaction?
यस
जी
सर.
जी क्या डिफरेंस क्या
सर ये
है?
इम्पल्स टरबाइन नहीं होगा सर?
ये 50%
सर
इम्पल्स
रिएक्शन तो
होता है
सर
और 50% रिएक्शन होता है। ठीक है, जैसा कि मैंने पहले भी अभी बताया है कि 100% रिएक्शन नहीं हो सकता, ये 50% इम्पल्स होता है और 50% रिएक्शन टरबाइन होता है। ठीक है, प्रोसेस टरबाइन।
सर सर हमने सर थर्मोडायनामिक्स में पढ़ा था कि वो रिएक्शन टरबाइन में सर वो होती है जैसे वो स्टीम बेसिकली लीकेज होती है, वो भी साथ मूव कर रही होती है
बिल्कुल
सर.
ठीक
इसमें
है।
सर वो फिक्स सर वो नहीं
नहीं,
सब इसलिए सर
फिक्स से फिक्स से आगे तो जो रनर है वो तो मूव कर रहे हैं ना, वो रोटेट कर रहे हैं। ठीक है,
या सर शाफ्ट के ऊपर सर बना हुआ होगा शाफ्ट के ऊपर.
शाफ्ट के ऊपर जी ये जनरेटर है ये।
यस सर.
ठीक है, डज इट आंसर योर क्वेरी या मैंने आपको क्वेश्चन नहीं समझ पाया ठीक तरह से?
सर आ रहा है सर, आ रहा है थोड़ा सा आगे सर.
चलिए ठीक है, इफ यू हैव गॉट एनी फर्दर क्वेरी वी कैन डिस्कस आफ्टर दिस लेक्चर एज वेल, क्योंकि इम्पल्स फोर्स हमेशा जब भी जनरेट होती है वो इट वुड बी जनरेटेड ड्यू टू चेंज इन डायरेक्शन ऑफ द फ्लूइड, राइट? एंड रिएक्शन फोर्स इज kind of if impulse force, if I can summarize it, impulse force is due to Newton's second law of motion, and reaction force is created due to Newton's third law of motion. ठीक है उमेर? So basically, in the impulse turbine, because we say that there is no change in velocity magnitude, but there is only change in velocity direction. So that's why we call it impulse force. And in the reaction case, there is a striking of that fluid, so that it can lose some of its pressure energy, and that pressure energy is converted into kinetic energy of the rotor blade. So as it was shown in this video as well, that there is some kind of change in kinetic energy of the fluid as well as the pressure energy. So we can call it 50% impulse and 50% reaction turbine. ठीक है उमैर खालिद?
यस सर.
Okay, thank you. So now we were discussing different four different types of reaction turbine. So the first type we discussed, that is radial flow compressor turbine, in which the flow enters the runner blades. So this is the runner blade here, where the mouse cursor is. This is the runner blade, and this portion, which is this kind of attachment, that is the band, which is kind of a ring shape, which is encompassing the or surrounding the runner blade. And then if the flow enters the runner at some angle between radial and axial, here you can see that is not strictly radial as in this direction, right? So it is kind of at an angle. So now we call it Francis mixed flow turbine, right? So this is the second type of turbine, and then as I mentioned earlier, that Francis turbines are more suited for heads, that is between the high heads of Fulton wheel turbines and the low heads of Kaplan turbines, right? And then some hydro turbines engineers use the term Francis turbine only when there is a band on the runner, so which is the figure on the left hand side. So engineers usually call it Francis turbine when we have got a ring outside which is kind of surrounding the blade. And if there is no ring, then we call it kind of Kaplan turbine, right? So if the runner has no band and flow under the runner partially turned, it is called a propeller mixed flow turbine or simply a mixed flow Kaplan turbine. Right? So here you can see that there is no band here. They are not attached to the blade, so it's kind of without band or that thing. So we call it simply propeller mixed flow turbine. And if these runner blades, they are kind of at a downward location, which is shown here. So now you can see that the turning of the fluid has occurred completely, and it enters the runner blade in the axial direction, and it exits the blade also in the axial direction. So we call it axial flow Kaplan turbine, right, or propeller turbine. And then there is another distinction between propeller turbine and Kaplan turbine. So what is that distinction? That is that Kaplan turbines are called double regulated turbines because the flow rate is controlled in two ways. By turning the wicket gates are basically those drive vanes, and by adjusting the pitch on the runner blade. Now, how can we adjust the pitch of the runner blade? Maybe I would come to it maybe in a minute. So, and then the second classification is propeller turbines. They are identical to Kaplan turbines except that the blades are fixed. So it means that blade pitch cannot be adjusted. So pitch means the distance between the two blades from where the flow is going to travel. So how can we kind of adjust it? Let me show you another video for the Kepler turbine as well, and then maybe it would be more clear to you. Let me yeah. Okay, so when the flow is going to strike here, then there would be two components of force. So one is in tangential direction and one is in the axial direction. So because the flow is striking here, it would have higher pressure here and lower pressure on the bottom side. So that's why there would be a change in pressure, and that would give force in the tangential direction, which would rotate this blade. Yeah. Now you can see that they are going to when they are going to close, then volume flow rate would be a little bit less. Okay, now this is the second part where it is saying that they are adjustable, and the first thing they mentioned before that it has got a twist so that the angle of attack is kind of optimal. So they would show you it maybe in a couple of seconds. Yes, this one. So now from this way we get and they would be closed. They would be kind of closed. So this was great about the Kaplan turbine. So they are kind of without that thing. So I hope that you can have a better idea of different types of turbines, their operations, and what are the critical parameters which affect their performance in operation. Right. So uh, uh, we discussed these the types of turbines. Now, where are they used actually? So they are not used in isolation. They are usually used in parallel arrangement in hydroelectric dams. So like Talbita Dam, Mangla Dam. So it is better that if we can see that where they are installed in hydroelectric dams. So uh, a schematic of hydroelectric dam it is shown here. Right? So it is the same for all the dams, the hydroelectric dams which are present in Pakistan. So there is a kind of a reservoir of water, uh, and then there is a head gate. If it is closed, like if we want to do some kind of maintenance on these generator or turbine, then we close this gate and then we can perform the maintenance. Like I think maybe a fortnight back there was some kind of power shortage in the entire country. So that was due to some kind of shortage of water as well as some kind of maintenance activity going on in the Villa Dam, I think. So if we want to close the operation of dam, then we kind of close this head gate. So we can control the volume flow rate which is coming on the turbine by the position of this head gate, right? So the path from the head gate to the up to the turbine we call it penstock. Okay, so first of all, here it would be better if we can talk in terms of head. So here, if we take an arbitrary reference point, which is z is equal to 0, then we can say that that a that is the net total head available in that dam. So it means that that is the maximum head we can use to produce electricity, right? But actually, we are the head available for the electricity production. That would be the change in elevation head at the entrance to the exit, which is ZA minus ZE. E is the point which is outlet to that dam. So ZA minus ZE, that is the gross head. But because there are some frictional losses as well in the dam, so actual net head which we usually use that is a little bit less than the gross head which is shown by this net head H, right? So which is the difference in these manometer readings at the inlet and outlet of the turbine. So where is the rest of the head? Those are consumed with the frictional losses, right? Because the water has to flow from this reservoir to the turbine through penstock. So you can see that there would be some viscous losses like we discussed in chapter number 8 when we discussed about internal flows. So those are the losses which are unavoidable. So we have to kind of live with that. So now if we can go through I have just explained uh, the overview of this schematic of dam. Now we can go through the next slides explaining different parameters of this hydroelectric dam. So the overall or gross head, which is shown here, that is defined as the elevation difference between the reservoir surface upstream of the dam, which is point A, and the surface of the water exiting the dam, which is at point E, right? So that A minus that E. So this is the maximum head which ideally can be used for the power generation. But because this is viscous flow, so the actual net head available would be a little bit less, and that would be given by the head available at the entrance of turbine minus head available at the outlet of turbine, which is point D. So point B is the inlet of turbine, and point D is the outlet of turbine, and that would give us the actual net head available for the power production. So we have got generator installed here in front of turbine. Okay. So if there were no irreversible losses, so what are the irreversible losses? Those are the frictional losses that the water would experience when it flows from this reservoir to up to this turbine. So those are the frictional losses involved in the system. The maximum amount of power that could have been generated per turbine, that would be equal to rho into G into V dot, that is the volumetric flow rate through this penstock, which of course that can be controlled by the position of this head gate. So this head gate, if we want to close it, there would be some pressure on this head gate. So how can we calculate that? The forces which are being applied on the this head gate, that would be calculated by your knowledge of chapter number 2, which was hydrostatic distribution of pressure. So I am talking about the case when this is fully closed. Because it is fully closed, so it means that there will be some kind of pressure force acting on this head gate. So we need to make sure that head gate can sustain those forces. So it means that the material and the position of this head gate should be such that it can withstand all those forces on this head gate, right? And that was just to kind of give you idea that where we can do that hydrostatic distribution of pressure, which you have done in your FM1 during chapter number 2. So that is one application that we can calculate the stresses on this head gate, which is due to the hydrostatic pressure distribution. Right. So after that, water flows from the point A upstream of the dam at highest elevation, that they add volume flow rate V dot through a large tube through the dam called the penstock. Right. So this is the penstock from where the water flows, and then, as I mentioned, that the actual power flow to the penstock can be controlled by closing a large gate valve called a head gate. So I have explained that if a pitot probe is inserted at point B at the end of the penstock just before the turbine, the water in the tube would rise to a column height that would be equal to energy grade line. Energy grade line and hydraulic grade line. Those are the basic concepts which is what I think in chapter number 3 or 4 in your SM1. At the inlet of turbine, and then this column height is lower than the water level at point A. Why that? Because there is some kind of frictional losses when the water flows through this penstock and at its inlets. Because we also studied the inlet losses as well in terms of KL, if you remember in chapter number 8. Now the flow then passes through the turbine, which is connected by a shaft to the electric generator, and then after passing through the turbine runner, the exiting fluid point C still has appreciable kinetic energy and perhaps will. So, and there would be some kind of spill, and to minimize that spill, there is kind of those guide vanes and stay vanes, so we can reduce the spill. So to recover some of this kinetic energy, which would be wasted, there would be a draft tube here. So draft tube, as we mentioned, as it was also mentioned in the video as well, that it has got a diffuser type shape. So it would increase the static pressure, right? So the draft tube flows and turns the fluid horizontally while increasing the pressure. So why we want to increase the pressure? To avoid cavitation and to recover the losses as well. So water flows downstream from draft tube into uniform cross-section conduit, which is called tail race. So this is the tail race, which is of uniform cross-section. So the net head across the turbine is EGL in, which is this, and EGL out, which is this head is net head at. So the net head of a turbine is defined as the difference between the energy grade line just upstream of the turbine and the energy grade line at the exit of the draft. So it means that we are talking about EDL in and EDL out. So if you why it is greater than this, because there would be some velocity as well. So from here to here, that is the dynamic head. This is the elevation head, and from here to here, that is the elevation head. Right? Energy grade line and hydraulic grade line. I hope that you get that. If I can tell you the relation between these two, that is, I think, energy grade line is the static head plus dynamic head plus elevation head. While the hydraulic grade line HGL, that is static head plus elevation head. So HGL, we can say that EDL is equal to HGL plus dynamic head. I think you must have gone through this concept in FM1. Okay, so this was it. So at the drop tube exit point D, the flow speed is significantly slower. Why is that? Because it has got a difficult type arrangement. So all the remaining kinetic energy leaves into this tail course that is going to be dissipated. This represents an irreversible head loss and is the reason why EGL out is this EGL out that is greater than this ZE because of this irreversible loss. And okay, so this was the function of this hydraulic dam. So basically, usually we use Francis turbines here, right? So as it was, yes.
सर स्टैटिक हेड और एलिवेशन हेड में क्या
अच्छा, स्टैटिक हेड और एलिवेशन हेड में क्या फर्क है उमैर? Is that the question? Okay. Okay. Static head, static pressure head, if I talk about static pressure head, that is due to the collision of fluid molecules. Okay. So this is the pressure head value which you can see from the steam table, right? So static pressure values you can see from the P upon gamma. So this value, if we talk about static head, that is P upon gamma, right? So what is P? That is the pressure which you can see from the steam table, right? And what is dynamic head? Dynamic head, that is the pressure head which is due to the bulk motion of the fluid, V square upon 2G, right? Which means that the bulk motion of the fluid is here. This is the molecular motion. Here, the static head, we call it due to the molecular motion of the fluid. And it is due to the bulk motion of the fluid, right? Like all the molecules, they are traveling in, let me give an example of this. Maybe you can understand that. If we have got a room in which we have got a certain gas, so in this case, because it is not going to move in a particular direction, so there was a pipe here, so we have closed it by the use of some valve. So it means that when it is this room is closed, so the pressure which is going to be exerted on the wall due to this molecular collision with the wall, that would be static pressure, right? But if we open this wall, what will happen that the gas would start to flow here. Then even then there would be some pressure of this gas that would be less than when the bottom was closed, and a part of it would be converted into dynamic head, which is due to the motion of fluid. Dynamic head. So it means that v velocity which is going through this, and then if we take a certain reference point, that is the elevation head. Does it give you an answer about the three heads we usually use in fluid mechanics? Math?
Yes, sir.
Okay, so that's fine. Okay, so let me conclude it, the lecture, and then draft two we discussed about the net efficiency of the entire hydroelectric plant is the ratio of actual electric power produced to the ideal power. So ideal power would be based upon this gross head, and the actual power would be based upon this net head, which accounts for the frictional losses inside this dam. So while the turbine efficiency is based on net head rather than the gross head, as I mentioned. So if we discuss the turbine efficiency, that is the brake horsepower divided by the water horsepower. Water horsepower is the maximum energy which is available, but the brake horsepower is the power which we collect at the shaft. which is connected to the generator. So brake horsepower would always be less than the net horsepower which can be provided by the water, but because there are certain frictional losses, so that's why the net head S would always be less than the gross head, which is at gross. So it is, if I give an example, very kind of analogy. So when you would be kind of when you in your professional life you would have some job. So when you would have some job, there would be a gross salary, and then there would be some taxes. So after that, you would get some net salary, which could be, so in ideal case, your salary should be gross salary, but because there is some kind of taxes involved, so they are kind of irreversible losses which you have to bear, and you would get some net salary. So that is the same thing in case of turbine. So you can always think about these engineering applications in terms of analogies which we face in real life. So the turbine efficiency is the reciprocal of pump efficiency, since BHP is the actual output instead of the required input. So in case of when we say that efficiency is the actual output divided by required input. So for the pump, it is the water horsepower divided by the brake horsepower. So this is the actual useful work which is imparted on the fluid in case of pump, and brake horsepower is always greater than this useful work which is imparted on the fluid. While for the turbine, it is totally the inverse. So as you also see in your thermodynamics that when you define the isentropic efficiency for the pump, it is always the actual input input work divided by the it is for the pump, it is ideal input work divided by the actual input work, and for the turbine it is the reverse. So it is the same thing. So most large hydroelectric power plants have several turbines arranged in parallel. So this offers the power company the opportunity to turn off some of the turbines during times of low power demand and for maintenance. Right. So as we discussed for the pump arrangement, that we can arrange pump in series and parallel. So similarly, we can do the same with the turbines as well. So in hydroelectric dams, there are usually many turbines attached in parallel. So that in winter, if we have got less power requirement, we can switch off some of the turbines, and then if there is some fault in one turbine, we can switch off water supply to that turbine for the maintenance. So now I would give you some examples of actual hydroelectric dams which are installed in maybe in all over the world. Like the Hoover Dam in Boulder City, Nevada, they have got 17 parallel turbines. So we are talking about Francis turbines which are installed in parallel, 52 of which are identical large Francis turbines that can produce approximately 130 megawatt of electricity each, right? So 15 into 130 plus 2 addition. So it is kind of the maximum gross power head is 590 feet. The total peak power production of the power plant is 2 gigawatt, like 2000 megawatt. So this is the elevation head, and then here we have got those. At this we have got those turbine and generator installed in this structure. So now let's move towards our national hydroelectric dam. Like in Turbella Dam, we have got 17 parallel transfer turbines and having capacity of 175 megawatt each. Four, they are a little bit larger, which has got 432 megawatt, and then three have even larger, which is 470 megawatt. So the maximum gross height is 470 feet, which is the difference in elevation between the inlet to the outlet, and then the total peak power production is 3400 megawatt. Similarly, if we talk about Rajiv Dam, they have got 5 pressure turbines having 290 megawatt. So it is less than, I think, less than, it is approximately for 1415 megawatt, but the Villa Dam, that is kind of 3400 megawatt. So the Villa Dam, it is a little bit bigger dam as compared to Rajiv Dam. So that is 1450 megawatt, right? And then it is situated nearly 7 kilometers of Villa Dam. So it is all in the vicinity of this area. Then Mangala Dam has got 10 parallel sensor turbines having capacity of 100 megawatt each. So it can kind of produce 1000 megawatt peak production. right? So these were some of the examples of the dams which are installed in Pakistan. So all of those dams they have got fresh turbines installed in them. So as it was also mentioned in the video that it accounts for 60% of hydroelectric power generation all over the world. So it is gas turbines and they are very normally used in hydroelectric dams. So I hope that this lecture would give you a brief overview of turbines, their principle and different components, how water comes, and then there would be some more detailed in-depth analysis about the blade design and how can we calculate those power generation for, and how to design a blade. So uh, those involve some kind of those knowledge of turbo machinery, velocity triangles. So we can always do those theoretical, what do we call it, theoretical calculation to roughly see that what is the power generation. But because in those velocity triangles we don't know certain velocity, which would come from, by the actual experimental value. So it means that our analysis is kind of limited analysis. So theoretical analysis, there are certain limitations. So all these velocity triangles, for instance, require some velocity information, uh, which is not available before we put those turbines into operation. So either we conduct experiments, or second thing which we can do, that we can do kind of CFD analysis, like computational fluid dynamics analysis. The project of the same which I gave you as a term project. So usually in industry, people usually use these kind of CFD tools just to have a better design of a pump turbine. But as you must have experienced that it is also very time consuming and it requires quite large computational resources. So there is always a trade-off between time and computational resources. So that is where and the real challenge of engineer as a design engineer comes into play. That we can combine the theoretical knowledge with the experimental and the numerical CFD tools to just to design the best possible arrangement for a particular engineering application. So I think today's lecture is up till here.